Hello everyone, this is Mehreen Tahir, and today we will be talking about federated learning, which is considered to be the new dawn for machine learning for IoT devices. I've mostly been introduced, but let me go through the introduction once again. I'm a PhD student and a researcher at SFI Center for Research Training in Machine Learning based in Dublin City University, Ireland. I'm also working as technical specialist and author for Content Lab. And I've been recognized by Code Project and C Sharp Corner as MVP. You can see my shirt as well. And previously, I've also worked as an author for Pact Publishing. So that is me. To give you an overview of what we will be talking about in today's session, let's go through the agenda quickly. First, we will just scan the edge and IoT ecosystem. We will talk about the emergence of intelligent devices. Are they very new, or is it something that has been there for a long time? We will talk about the protocols for device communication. Then we will move forward with federated learning and discuss the scenarios where we would want to apply federated learning and the scenarios where we would not want to apply federated learning. We will also talk about the challenges that federated learning face these days, and then I will leave the floor open for any questions that you might have. Um, and this is going to be a high level overview since it's an advanced concept, but perhaps we can follow up with the hands on lab later on. Contact Simon for that. Okay, let's begin. So, first of all, why are we even interested in IoT devices and market? Uh, To highlight its importance, let me give you a few numbers. So McKinsey has reported that there will be 11.1 trillion market value by 2025. That is a huge number. We're talking about trillions. Bosch has reported for 14 billion connected devices, while the Cisco says there will be 5 billion connected devices. Gartner had came up with a number of 309 billion IoT supplier revenue and 109 trillion economic value. And IDC says there will be 7.1 trillion IoT solutions revenue. This is just the market number. So all the cash that we are talking about. So you know that there's going to be a huge scope. And let's see what MIT review. This is from 2014. The only reason I wanted to highlight is so you have the idea where we were standing like 10 years ago and where we are standing right now. So it says the machines that would go online would exceed PCs and smartphone. We're talking about like connected things. These things include all the sensors, all smart devices, however small they might be. So in 2010, if you see, there was a very small number of connected devices. But if we move along the right to the right to 2020, the number of these connected things have certainly surpassed even the cell phones that we are using right now. And this is we are talking about the numbers in billions, around 30 billion devices, and that was 2020. Imagine what would it be like in 2021. Global IoT market has increased by 38%, and this is year to year growth we're talking about. And by 2020, we had a 500 billion US dollar market for IoT devices. And if we talk about the subsectors for these market share, we are mostly interested in developing smart cities, which comprises 26%. Then there is industrial IoT, connected health, smart homes, self-driving cars, any type of wearable devices, or smart utilities. This is all part of this IoT market. So industrial IoT and smart cities are topping the chart, but we're also mostly the world is now also moving towards the connected health and smart home. Connected cars and self-driving cars still have a scope, so if anyone of you is interested, please go ahead. So what does this imply, like all those numbers? First, there's no denying that there is a huge IoT storm right here, and we're talking about managing billions of connected devices, and they might be trillions in the near future. A huge deluge of data has been observed in 2020, and which means we're talking about around 1.5 GB of traffic per day from average internet user. This is the amount of data that you were producing on average per day. And then if we talk about smart hospitals, around 3,000 GB data per day, self-driving cars, and we're talking about each one, had 4,000 GBs per day. Radars and sonars almost were producing same 10 to 100 kbs per second. And now we are moving to per second, how it was going. GPS around 50 kilobytes per second, UDORs 10 to 70 MBs, cameras 20 to 40 MBs, and then connected aircraft were producing 40,000 GB per day. But the connected factories, where mostly sensors are installed, like small sensors, were producing thousands and thousands of GBs data per day. Now we need to make use of this data and we have to manage all these connected devices. How do we do that? Before going there, let's talk about how this market evolved. So, these connected devices or intelligent systems are not new. People were using sensors in their factories even in 1980s or before that. If anyone of you is old enough, they might know the PLC, SCADA, automated uh, sensors for temperature and humidity and everything. They have been there since 1980s. So we are talking about electrical and magnetic sensors, which were connected to logic controls. These sensors were previously dumb, but they were connected to intelligent hubs where mostly decision making was happening. And also, these control hubs got more distributed and miniaturized with microcontrollers. The biggest push that this industry observed was after the SoCs and ARMs were made cheap. Why? Because it mostly reduced the cost for intelligent nodes, and also computing schemes were changed totally. So you don't have to be a pro to interact with IoT devices now. If we look at the IoT devices like these days, um, most of the devices has local CPU. They have memory. They have GPS, GSM, LTE. Although there might be small packages of these, but almost every IoT device has all these. Again, like I said, small packages, so CPU is not going to be very powerful like your laptop or computer, but it will be sufficient for the IoT device. Also, the memory is pretty low. We're talking a few MBs to few GBs at best. I think 2 3 GBs, that would be it. And then the links are very slow and lossy. Most of these devices would be battery operated and mostly be installed at some remote locations. And these IoT devices include Arduinos, BeagleBoard, Raspberry Pi, all those cheap boards from China, which include ESP8266, ESP32, and etc. Any one that you can think of. Okay, so how do we communicate with all these devices? Biggest communication is the key. Since these IoT endpoints are now intelligent, they have their own brain, like CPU. So we would need a communication protocol. And this communication protocol should be able to work on low power and lossy channels. Most of these protocols are modeled after the web style protocols, such as HTTPs and WebSockets with proxies or direct use of message queues. Scale might be much smaller because we only need to transfer small packets, and the transfer rates are lower. But still, these communication protocols are there. And what types of communication protocols? We are talking about device to gateways, which means the communication that will be happening between device to network gateway. Then there will be device to device communication, which would be relay type. um, Gateway to cloud communication, which is the typical cloud interface these days, and there will be device to cloud. So, cloud to device and then device to cloud can also happen, but that is possible if the cloud is at the edge. We'll talk about that. So, if we look at the major communication IoT protocol these days, direct messaging, message queue, telemetry transport, MQTT. Most of you, if you have been working with IoT, might have worked with it. It is lightweight, small footprint, PubSub type, and it requires a message broker. It is data agnostic, so means there is no standard data structure. It's just text-based label and info. Then messages will be delivered with or without confirmation. Or guarantee, but many deliver just fine, but once. And then there is a constrained application protocol, COAP, lightweight. It's a fast HTTP, tens of bytes over internet or over thousands of bytes in typical HTTP over TCP IP. This protocol was specifically designed for constrained nodes that have very limited resources, and it also has RESTful interfaces, and it may contact device to cloud or via proxy to cloud or device to device. So, and there are a few other protocols which include cloud web based or V2X protocols, and there will be different communication mediums, which means we could be transferring data over wire or over wireless, or we could be using different communication protocols. The reason we talked so much about these protocols and technology is, you know, there is a huge number of protocols, but how do we decide on one? How do we converge? That is the main question. So, if any of you have worked with machine learning, you guys would know the classical machine learning works in a way that you train the model on a central server, and then all the data goes there. Model is trained on the central server, and this is where all the decision making is happening. How do we do that in IoT environment? Are we going to send all the data from each IoT device to the central server and then get the prediction? But if you're sending all that data back to central server, that means there would be a communication overhead, a huge communication overhead, because they have limited resources. So, what do we do? Another thing that concerns us is privacy. So, all these intelligent systems, like you want to make an album for your kid to easily share with grandma, or the text completion tasks or next word predictors, or if you want to write better emails, analysis and all those, it happens, but it just need access to your data. And how do we know that that data would not be leaked to some third party? I hope you're aware of the controversy that had been happening with WhatsApp and Facebook, that they have been sharing data with the other companies. So where do we stand on privacy terms? What do we do again? Okay, so a solution could be to develop intelligent systems, which means that each system or subsystem can make decision based on variety of stimulus. Distributed decision making is what we're talking about, because we don't want to traverse the data through long distances with so many devices involved. So what do we do is, we bring something to our device. We try to implement in place decision making, so the decision could happen right there, and this intelligence would be driven by data, IoT enabled data collection. But how do we do that? Can we use edge computing? Can we use distributed machine learning? or where do we go from here? Okay, this is where the federated learning comes in. This is a very special case of distributed machine learning. What happens is we are interested in enabling devices to learn from each other. So there is IoT at the very base level, which are connected edge devices. Then there is AI, driving intelligence from device data. We want to train models based on the data and then get prediction or do something intelligent. And on top of that is federated learning because it will help us improve the performance at the edge. So edge, okay, let me clarify one thing here. Edge could be your cell phone. Edge could be any endpoint where you want the decision to happen. It could be the access point for the cloud. It could be your cell phone. It could be any other IoT device which is intelligent enough. So, more specifically, what we are doing here is we are we're talking about a network of nodes. There are all those nodes with the central server, but instead of sharing data with the central server, we share model. We don't send data from node to server. We would send our model to server where it would be aggregated and sent back to nodes. I know that is a lot to take in, so let's break it down and let's try to understand what is happening here. First, let's see there. So imagine there are connected devices. Let's say we have cell phones, okay, from four of the people that are watching us live right now. And there is one central server, and the server has untrained model. Okay, there's just some random machine learning model. Let's say we want to predict the next word, so we have an untrained model sitting at the server, and now the cluster of IoT devices is comprised of four cell phones, which are there. We're just calling them node at this point. What we will do is we will send a copy of that model which was sitting on the server to each of the node. So if I am in the node, I would receive a copy of that model on my cell phone. If you're in the node, you would receive a copy of that model on your cell phone. So each device would receive a copy. Now all the nodes in the network has that untrained model. Okay. In the next step, what we're doing is we are taking data from each node, but by by taking, I don't mean that we are sharing data. Every node has its own data on which it is going to train a model. So if I'm talking about myself, the data from my cell phone, which word am I using, what am I writing, what I want to say, it will use that data, and your cell phone would use your data to train the model on your phone, not on the server. Sorry about that. And then, okay, so we were talking about training. So each node is training the model to fit the data that they have. So previously it was this. Just pay attention to how the line is on the nodes. And now it will train the data it will train the model accordingly to its data, and this is how the training is happening on the nodes. In the next step, each node would send a copy of its trained model back to the server. Now, again, sorry, I don't know why am I receiving so many emails. So the server now would combine all these models received from each node by taking an average. Okay, it will aggregate, and then it will train that uh, central model. This model, which is now trained by aggregating the models from each node, now captures the pattern in the training data on all the nodes. It is an aggregated one. Okay. And the last step, what happens is the server will now send the updated model to each node again. And the whole process would be repeated all over again. Once, so the first step is server is going to send the model to each node. Node would train the model locally using their local data and will send a copy of that updated model to the server. Server will receive each copy from all the nodes and then aggregate the model. Once it is aggregated, the server will send the copy of the updated model back to the nodes. And note that there is no data sharing happening. Everything is being achieved at the very edge. We're doing it on your end. So, no data sharing means there is privacy preservation and also very less communication overhead. So, the model that I just explained is known as vanilla federated learning or federated averaging. This is a snippet of the code. I didn't want to bring in the code at this moment because this is just a lot to take in. This is just to make the idea clear that what is happening. We are receiving the model. Okay, one more thing. I think I should clarify this. We are not actually sending the whole model. We are exchanging the parameters that it is trained on. So we don't have to share anything to avoid the communication overhead. So what is happening is the central server will receive parameters from each node in the network, and then it will aggregate its central model, and that's where we get our updated central model. An example of this, like I had explained previously, is the next word predictor with the privacy concern. So, Google has been actually the federated learning concept was introduced by Google, I think, in 2017, and they have been implementing it in Gboard to give a more private experience but more personalized keyboard experience to the users. Okay, I hope that this is somewhat clear. If not, I will leave the floor open for the question later on, so please feel free to ask. Here we will talk about when we would want to apply federated learning. Of course, foremost option is when we need privacy, where we don't want to share our private data with anyone. It could be a retail company, it could be just the user. So this is where we would apply federated learning. Then, if there are bandwidth or power consumption concerns, then federated learning could come in since we are not actually exchanging the data. So we won't be using much of the bandwidth or power. We are just exchanging the parameters. And if there is also a high cost of data transfer, then federated learning is a yes. There are cases when we don't want to apply federated learning. Um, those cases include when more data won't improve your model. So, when working with machine learning, you can actually construct a learning curve. And if you see that more data is helping in improving your model performance, then you would wanna apply the federated learning, because we are talking about data from each node, and that is huge amount of data. Um, Also, so this is almost related to data. This federated learning is driven by data. If additional data is not correlated, or it's not helping improve our model, we don't want to apply federated learning. Or if we have already achieved the ceiling, then ceiling means we have achieved the desired result. We have the model uh, the way we want it, like just the performance we wanted. Sorry, my bad. Okay. um and a few considerations before we want to begin. First thing is we want to benchmark our performance, how much accuracy we are talking about, how much loss can we take in. So this performance should be a benchmark first, because the training, to and fro training, the server will keep on sending the parameters to nodes will keep on sharing their parameters back to central server, will keep on happening until we have received our desired result. So the foremost thing is we want to benchmark the performance. Then we want to make sure that performance is improving with more data, and the models can be combined meaningfully. Okay, so if there is some if we are talking about a banking sector, there could be a meaningful scenario where we would want to combine models from, let's say, the statement, how the purchasing history of the user from their shopping, so we could predict what user would most likely to be buying next or something. So like there should be a meaning in the combination of the models that we are talking about. And then we the nodes that we're talking about in the network should also be able to train model and not just predict. And last but not the least is we want to determine how we will be transferring these models, which protocol we would be using, how much bandwidth we would be consuming, and everything. Okay, so are there any tools that will help us build federated learning models? Well, yes, there are. First is Open Mind. It's an open source community focused on researching, developing, and promoting tools for secure, privacy preserving, and value aligned artificial intelligence. I literally just Googled it and pasted it here, but it's an amazing community for the researchers. If any one of you is interested in research or in privacy aspect of the machine learning, please go ahead and check them out. Then there is PySif. This is a library for privacy preserving deep learning. And Google Google has also introduced TensorFlow Federated, which is the API and also the core. Both are available. What it does, it wrapped TensorFlow model in included federated learning implementation, and of course, this is a high level where you don't have to worry about the nitty gritties and very small details. It will handle it all by itself. But it also pays attention to the separation of concerns of model, communication, and everything. So, okay, all sounds good, but are there any challenges? Well, yes, there are. First is system issues. Power consumption is still a challenge because, like I was giving you an example of training on your phone. So we don't want to consume, or we don't want to compromise the performance of the edge device. We don't want to drain the battery of your cell phone. So how much power we would be consuming over edge devices and how we would be doing it when we will be training the model. This is all a question. Well, there are approaches. Let's say they want to train the model when you're not using it, when you're sleeping or something. But again, we don't want to drain the battery or something. So that is still an open question. Another system issue is dropped connections. So how are we interacting the nodes and the servers? How the communication is happening? If it is happening over the internet, maybe someone has turned off internet. Like I usually just turn off my internet when I'm going to bed. So which means I'm not giving it any connection or any time to train the model. How are we going to deal that situation? Another open question. And then there are stragglers. Stragglers are basically the devices that failed to train, that failed to respond in the given time window, or they failed to complete the model training in the given time. So this is another question. Uh, and privacy is still a concern. How? Okay, we are not sharing data, but we are still sharing model updates, parameters, and adversaries might not be able to inspect data, but they can inspect the model, and they can poison your model. So if there is some poisonous node, some hacker What are we going to do with it? How are we going to deal with it? How we will preserve the privacy? Well, there are approaches which include uh, wrapping it up. Sorry, I just lost the word. But so we wanna code it, encrypt. Sorry, yeah, got it. Encrypt. So there are encryption based techniques that we might be using, but again, that includes a little overhead. So if there is a better way to preserve the privacy and save the bandwidth at the same time. Open question. If anyone is you interested. Okay, so this is almost it. If you are interested in federated learning, go check it out on Google. They have pretty good blog on it. There are communities building. This is an advanced concept and is still developing. So you might face few challenges. In that case, you can get in touch with me on my email, on my Twitter. Find me on C Sharp Corner. Drop me a text, an email, whatever. If anyone of you is interested in getting to know more, or want to discuss or want to explore some research opportunities. Um, yep, that would be it from my side.